Welcome, everyone. Today, we are exploring the intersection of reliability-centered maintenance and criticality. The core message of this session is that the name of the asset shouldn't dictate your maintenance plan. Rather, the specific failure mode is what truly owns the strategy. We will break down how function, failure, and consequence lead us to the most effective strategy for every asset in your facility. Why does strategy choice matter so much? Recent NIST survey data shows that while advanced maintenance like predictive techniques can lower defect rates by up to 87%, it isn't a magic moment. RCM helps us avoid applying expensive technology indiscriminately. We must remember that association is not a strategy rule. The correct mix of maintenance still depends on how a machine functions and how it behaves when it fails. To illustrate our proposition, consider that a single asset could legitimately have 5 different strategies applied to it simultaneously. You might use condition monitoring for bearing degradation, time-based replacement for consumables, and run-to failure for a simple indicator lamp. The asset name doesn't choose the strategy, the failure mode does. At its heart, RCM is a decision process, not just a flavor of maintenance. It works by asking 4 fundamental questions. What must the system do? How can it fail? Why does that failure matter? And finally, what policy controls that risk at the best value? It moves us away from asking how much PM to asking what controls this specific failure. It is vital to distinguish between criticality and RCM, as confusing them leads to either shallow or excessive analysis. Criticality is a portfolio screen that tells us where to focus our scarce resources first based on business exposure. RCM, on the other hand, is the deep dive that determines exactly what should be done about each credible failure mode once we've decided to analyze it. The first step in our journey is understanding the operating context. We must always begin with the function of the equipment, not just its name. A strategy is only valid within a clearly defined operating context and system boundary. Context is everything. The exact same machine can carry vastly different risks in 2 different locations. Factors like duty cycle, demand, redundancy, and the local environment shape the consequence of failure. This is why you should never simply copy and paste a maintenance task from one asset to another without comparing their contexts. Before we can debate failure modes, we must draw clear system boundaries. For a boiler feedwater system, we need to know where the suction starts and where the discharge ends. Error here leads to missing interfaces, duplicate tasks, and confusion over who owns what part of the process. When defining a function, simple descriptions like pump water are insufficient. A usable function statement requires a verb, a performance standard, and specific conditions. For example, deliver 1,000 gallons per minute of feed water at 1,200 sig whenever boiler 3 is online. This gives us a clear yardstick for success or failure. Don't just look at primary output. An asset has many functions, and often the secondary or protective functions, like trips, alarms, or containment, carry the highest risk. We must inventory all functions, including quality, environmental, and support roles, to get the full picture. Functional failure occurs the moment required performance is lost. This can be a total loss, like no flow, but it can also be partial, like degraded output, or even hidden, where a standby safety trip simply wouldn't work if called upon. The equipment might still be running, but the function has already failed. We need discipline when writing failure modes. If we are too high level, like pump fails, we get generic, useless tasks. If we go too deep into molecular level physics, we create an unusable encyclopedia. We aim for the action level, where the description allows us to select a specific, defensible maintenance task. Clarity in language drives action. We must separate the symptom we observe from the failure mode and the root cause. While maintenance strategies are selected at the failure mode level, our defect elimination efforts continue all the way to the root cause to ensure the problem doesn't return. Let's use a boiler feedwater system as our running example. It's a high-duty system with low tolerance for loss. By looking at its specific demand, redundancy, and recovery steps, We can build a logic chain that justifies why we choose certain maintenance policies over others. Every task in your CMS should have a traceability chain. If you can't trace a task back through a failure mode and a functional failure to a required function, the PM becomes indefensible. This chain ensures every dollar spent on maintenance is directly linked to a business need. A good FMEA record tells a decision story. It's not just a data entry exercise. It connects the effect, what happens locally, to the consequence, why the business actually cares. This distinction is what allows us to choose the right policy. To keep the analysis honest, we follow the 7 SE-aligned RCM questions. Each answer naturally creates the need for the next decision, ensuring we cover everything from standard of performance to what to do if no proactive task is suitable. Now we move to criticality. Its purpose is to help us focus our efforts, not to prescribe exactly what to do. Criticality tells us where the analysis effort belongs, but it cannot choose the maintenance policy in isolation. Think of criticality as a business exposure decision. It determines the depth, urgency, and ownership of the analysis. Importantly, a high criticality rank doesn't automatically mean more PM. Even a critical asset can have valid run-to-failure modes if the specific failure has low impact. When scoring criticality, we should evaluate dimensions like safety, environment, and production separately. A total score should never be allowed to hide a redline safety or environmental exposure. We need to see where the risk truly lies. A risk matrix makes our rules visible. But remember, judgment makes the final decision. The matrix is a tool to structure a conversation among experts, not a machine to manufacture false precision. We must also consider exposure modifiers. Things like redundancy, how easy a failure is to detect, and how long it takes to recover can drastically change the apparent criticality of an asset. Always verify these in the field rather than assuming the design documents are still accurate. Criticality is a cross-functional workshop, not a solo spreadsheet assignment. To be valid, a score must survive the scrutiny of operations, maintenance, engineering, and EHAs. We should always challenge a rating by asking, what evidence would change this rating? Not every asset requires a full-blown RCM analysis. We should match the depth of analysis to the consequence and uncertainty. This ranges from rigorous facilitated RCM for high-consequence systems to simple documented run-to-failure for low-consequence items. Next, we focus on consequence logic. The consequence of a failure is what decides how hard we must act to prevent it. The same physical failure can be a non-event or a catastrophe, depending on the situation. Consider a bearing failure. In a warehouse fan, it's a minor comfort issue. In a process fan, it's a quality loss. In a boiler fan, it could trip the entire unit. The failure physics are identical, but the business consequence is entirely different. We must first ask, is the loss of function evident? Hidden failures are dangerous because the plant may not know its protection is gone until it's too late. These require a completely different management policy than evident failures. Consequence categories set the standard of proof for our tasks. For safety and environmental risks, we have zero tolerance for weak assumptions. For non-operational risks, the test is purely economic. Is the task cheaper than the repair? When dealing with safety and environmental consequences, cost is not the deciding factor. We must ask if the task is technically capable and if the interval is tight enough to keep risk within acceptable limits. If no maintenance task can do this, we must redesign. For operational consequences, we look at the total business case. This includes not just the cost of labor and parts, but lost production, quality yield, and the potential for secondary damage. Often, the repair cost is the smallest part of the total consequence. For non-operational, low-consequence failures, keep the economic test simple. Don't spend $1,000 on maintenance to avoid a predictable $200 repair. Choose the path of lower total consequence. Hidden failures are a multiple failure risk. The first failure, the hidden one, creates a period of vulnerability, and the consequence is only realized if a second demand event occurs. Failure finding tasks are designed to limit that window of vulnerability. Now we move to strategy selection. The goal is to choose the least cost strategy that truly controls the failure mode. Whether it's PM, condition monitoring, or redesign, these are outcomes of the process, not starting philosophies. Using a practical RCM decision tree helps prevent habit or vendor pressure from choosing our policy. We move through a sequence. Is it acceptable to let it fail? Can we detect it early? Is it age-related? Is it hidden? This logical flow leads us to the right strategy. Condition-based maintenance is powerful, but it requires more than just a sensor. You need a detectable precursor, the right technology, a monitoring frequency shorter than the warning window, and a plant capable of acting before the failure happens. The PF interval is central to condition monitoring. Detection has no value if it doesn't leave you enough time to plan and execute a response. We must always ask, what are we detecting, how early, and who makes the decision to stop the machine? Choose your technology based on the failure mode, not the vendor's catalog. Often, multiple technologies, like vibration and oil analysis, are justified together when the consequence of missing the failure is high enough. Time-based maintenance should only be used when there's a clear relationship between age and failure probability. If failures are random, simply shortening the PM interval won't help. It will just add cost and potentially introduce human error. When you do schedule a task, be precise about what it does. Are you restoring the component's resistance, replacing it entirely, or just discarding a consumable like a filter? Each has a different impact on the failure mode. We must be cautious. Maintenance can actually introduce the very failures it was meant to prevent. Every intrusive task breaks containment or disturbs settings. Before adding a PM, ask, what failure could this task actually introduce? Failure finding tasks are proof tests for silent functions like relief valves. The key is to simulate a credible demand and record the as-found condition. This is how we end the exposure period for hidden failures. Run to failure is a legitimate, controlled policy, not a sign of neglect. It requires a deliberate decision that the consequence is acceptable and that you have the job plans and spares ready for when the failure inevitably occurs. When maintenance cannot reduce risk to an acceptable level, we must turn to redesign or redundancy. Reliability can never be maintained higher than the inherent capability of the physical design. Every task must pass an approval gate. Is it technically applicable to the failure mode? And is it economically effective? If it doesn't pass both tests, we should revise it, reject it, or look for a redesign. Returning to our pump train, you can see how it carries a portfolio of strategies. Contamination is handled by condition monitoring, consumables by time-based tasks, and lamps by run of failure. We assign strategies to modes, then integrate them at the asset level. Analysis alone creates no value. We must now deploy these decisions into the plant's operating system. RCM only works when tasks, triggers, and materials are embedded in the way the plant actually runs. A system worksheet like this one for the boiler feedwater pump shows the end result. Clear, distinct decisions with specific triggers. This is what transforms abstract reliability theory into a concrete maintenance plan. Protective functions, like trips and interlocks, deserve special treatment. They often fall under regulatory standards like PSM. Never change a mandated test interval through RCM alone. Always use your formal management of change process. A strategy isn't finished until the task is executable. Every job plan needs clear methods, quantified acceptance criteria, and instructions on what to do if those criteria aren't met. We need decisions, not just activities. Selecting the right interval is critical, and each policy uses a different clock. Condition monitoring uses the PF window, time-based tasks use wear-out data, and failure finding uses risk-based protective availability. Don't just inherit old intervals from CMS. When loading data into your CMS, ensure you preserve the decision chain. Traceability allows for future audits and optimization. You should be able to look at a work order and know exactly which failure mode is meant to control. RCM must be a living system. A frozen analysis is a source of unmanaged risk. We must update our strategies whenever there's a new failure, a repeat defect, a design change, or new performance data. How do we measure success? We look at strategy quality, execution discipline, and business outcomes. PM compliance is a start, but the real test is whether functional failures are decreasing and asset availability is increasing. For those starting out, use a 90-day roadmap. Start with a bounded pilot project to prove the system. Screen in the first month, analyze in the second, and deploy by the third. This builds the capability and library you'll need for a wider rollout. Watch out for common traps. Don't try to analyze everything at once, and don't let consultants own the process. The cure for a failed RCM program is cross-functional ownership and a focus on executable, high-quality tasks. In summary, every asset deserves the correct strategy, but not the same strategy. Use criticality to focus your effort, RCM to make the decision, and strong governance to keep the system true over time. To continue your learning, I've compiled a list of authoritative standards and practical videos. These resources from SEE, NASA, and ISO provide the deep technical foundations for everything we've discussed today. Finally, all evidence and visual credits are traceable. The logic used here is grounded in recognized international standards and best practices. Thank you for your time, and I look forward to your questions.